makes things happy. And to make an amino acid happy in a peptide bond, you want there to be resonance in that peptide bond. And so therefore it needs to be planar. This means that you cannot rotate around the atoms involved in that peptide bond because you have resonance between this nitrogen, carbon, and oxygen. This is going to restrict the motion to the places around the alpha carbons when those amino acids are in a chain. You kind of can think about there being a plane from alpha carbon to alpha carbon. So here's a plane from this alpha carbon to here, and another plane from this alpha carbon to here. You can see that there are these kind of 2 points in which we can rotate. One is our psi angle and one is our phi angle. I like to remember that the psi, it kind of looks like a C on its side, and that's going to basically be telling you that's the one between the carbon-carbon, and the one between the carbon-nitrogen is our phi angle. Now, I don't think knowing which one's which is that important, but I do think that what's important is the idea that they're going to be restricted to specific places. And you'll see that these specific angle combinations of your phi and your psi angle is where you're going to see points cluster on a Ramachandran plot. Basically, a Ramachandran plot is where they go and they take, it can be for a single protein, it can be for a peptide, it can be from the data from thousands and thousands of protein structures, and it compiles these all together and puts all the angle combinations for all of the different amino acids in those protein or in the peptide and shows where they actually show up. And so you'll see that there are distinct places that are actually going to be like preferred regions. And then outside of that, the angles are less favorable. Another important thing is that there's places where things are like clustered. You can see that this is the region we find like our beta strands, and these are the angle combinations that are accommodable for alpha helices. So basically, you're going to have your range of motion be restricted by steric clashing. So you can see that when these overlap, you're going to get these red marks that's showing like clashing. That's a molecule's way of saying like, get out of my space. And so there's going to be this restricted motion, but you can see there's still kind of like a range. The reason why things get narrowed down even further is because you want to have the most favorable hydrogen bonding. So hydrogen bonds are very like orientation specific. They're strengthened when things are kind of like in a line, and so things to be in a line in a distinct structure, you need to take on more strict angles than just saying, okay, it's got to be in this region. And so that's why you kind of get things kind of locked in place a little more in those alpha helices and in those beta strands in terms of our angles. And you're going to be further restricted based on what the properties of the side chain are. So what amino acids are we looking at? So if we're looking at here, we've basically got an alanine. We've got our CH3 group here. It's not that big, so we can still kind of rotate a lot. But if we had something big and bulky, well, now the clashes will be worse, because although it doesn't look like there's that much stuff here now, when we go and we actually show the sizes of all the atoms, you can see that those are pretty darn big. There's not very much kind of room in order to rotate without having clashes. We can actually go and look at this. So I love this tutorial from basically Eric Martz, and there's an interactive version of it too that you can go and walk through. But it is a nice job of kind of like walking through the various natures. So a dihedral angle, that's just an angle between our planes. So like a dihedral angle would be like the angle between these planes. And so phi and psi are examples of dihedral angles. You can see that if you were to fix one of the angles in place and rotate the other angle, there's only going to be a set of regions in which you don't see those clashes. You don't get those van der Waals overlaps. That would be physically impossible. So the kind of like allowed regions are going to be points where you're going to find them cluster on a Ramachandran plot. But just because it's allowed doesn't mean it's like preferred. And so the preferred regions are going to be the places where you get like more of this density cluster. And you can see that basically there's only kind of like a range of things. So here we had fixed the psi angle at 165, and now we're going to be seeing which kind of ranges can we have for our phi. We can do similarly if we were to fix our phi angle, and we would see that we'd have like kind of two distinct ranges And those correspond to the beta strands and the alpha helices. What about in the center where we don't really see anything? Well, that's because you're going to have clashes at basically all of the positions. And so even when we're talking about glycine, or we're talking that can like be the most flexible, and you see these dots kind of like, you'll see the dots scattered all over. Basically, glycine it messes things up because it's too flexible, but even it cannot take on that angle of like having a phi of 0. So remember that the steric clashing is kind of limiting what angles it can take on. And so the bigger amino acids would be even more restricted. The smaller can have a little more freedom. But then even within that freedom, well, then they're going to take on more distinct angles. They kind of concentrate them more in these specific places, because that's going to be conducive to having these the hydrogen bonding that's needed to stabilize your alpha helices and your beta strands. And proline, well, that weird is just found like in a couple weird places. So basically, proline has that side chain that wraps back in on itself and limits its motion of the backbone even further and prevents it from doing hydrogen bonding. So you're really not going to find that guy in like a helix or a beta strand, but you might find it in one of the like turns between those strands. Bottom line, you single glycine and proline out on a Ramachandran plot. Often you'll have like a plot of all the amino acid residues that are like, except for glycine or proline. And so remember, residues just to mean a word that we call the kind of remainders that are left over when you link up amino acids. What was an amino acid we now call a residue. And so glycine and proline residues can be in like different places than the other amino acid residues in a Ramachandran plot. And they can, but the other amino acids like shouldn't be in those locations basically. So you often see, you'll say like, these are the Ramachandran angles for anything but a glycine or a proline. And if you have a dot that's outside of that, there might be something wrong with the structural model. So Ramachandran plots are a way in which kind of structural biologists test or check whether their models of the proteins that they make are kind of biochemically sound. And so you might see something like Ramachandran outliers when you're looking at a structural model. And so like, we'll talk much more about that, but not here. Just know that that's where that comes from. There are lots of great tools linked to. They are basically, you can play around with this. You can see if you were to go and just look at a single peptide, it lets you do things like look at little peptides, look at proteins. So you can see that here we only have fewer points because it's just a small peptide, whereas this is from 100,000 high quality general case data points. And so this is kind of like an average. But then you can also do it. You can see that glycine and proline take on these weird distributions. And you can go and you can look and you can see that myoglobin, well, it's got a lot of alpha helices. And we can look and we can see that if we go and we do a Ramachandran plot for that, well, now we're going to see more of the alpha helix regions. And concavalin, which is beta strands, well, now we're going to see more of the points cluster in that beta strand region. And if we have something that has a lot of each, we're going to see a lot of each in kind of in the classic areas. So that's kind of how you interpret these sorts of things. So you'll have a different Ramachandran plot for each protein or for each like amino acid or peptide or whatever you want to do. They'll have characteristic angles, or you'll see this kind of like a summary one from the data from a lot of different things.